Hello everyone, my name is Sandra Linda Bazapa Prophet, and in today's video I'm going to be walking you through one of the laid foundation of atomic structure and modern day quantum mechanics. Now we should understand that on the board is what we call the Schrödinger wave equation, and in Schrödinger wave equation I'm going to be taking you through the first dimension and three dimensions of the quantum mechanics as laid down by Erwin Schrödinger in the year 1926, right? So we're not going to waste any time. We'll just go straight to the point. Now we should understand that the Schrödinger wave equation is an equation, right, that talks about the wave mechanics and is based upon the idea of electrons, right, as a standing wave around the nucleus. That is to say, it talks about how quantum particles like electrons, how they behave. Now I'm going to be taking you through some of the derivations right now while we talk a step. Now I'll re-erase the board to create more rooms for the derivations. Okay? Now this is how it works. We start with the sign. Because remember, standing wave equation. Start with sign. This is how to call it sign, which is something like this. XIGH. Sign is equal to A sine 2 pi x over lambda. This is the first step. I'm going to give you step-by-step approach of the quantum derivation of Schrödinger wave equation. And this is the first one. Now remember, according to Schrödinger wave equation, you have to differentiate this first equation twice by saying the sine over the x with respect to what my x here. So remember, if you differentiate a, amplitude here is constant. So here you give me a, right, 2 pi over lambda, right? If you differentiate sine will give you what now? Cos. Then you put back everything here, everything that you're having here with respect to x. So it becomes 2 pi x over what now? Lambda. Take note, this is how it is. Amplitude is a constant. 2 pi 2 is also equal, so it comes here. So that's why you're having a 2 pi over sine, 2 pi over lambda cos 2 pi x over lambda. Now you also differentiate it again the second time, which is del square sine over dx square is equal to, remember, a is constant, so AC remains. Yeah? Now take note, if we differentiate this one here, again, you'll not be having here to be 4 pi square over lambda square. Because remember, now you're not having what we call, like if you differentiate this one again the second time, you're having a 2 pi lambda, you differentiate here times 2 pi over lambda. Right? Remember, if you differentiate cos will give you what now? Minus sine. Take note. If you differentiate sine to give me cos. If you not differentiate cos to give me minus sine. So that is what I'm trying to give you, the simplest approach. So here we're not giving that sine. Now we're having 2 pi x over what now? Lambda. So that's why I now have here minus a. 2 times 2 is 4. Pi times pi is pi square over lambda square sine 2 pi x over lambda. So this is what we have. So this was what I did here. So that if I differentiate cos, I will have negative sign, which is what I will put here. Then I'll put everything back here. 2 pi x over what now? Lambda. Now, what do we do next? We should understand that. Please follow me. Let me erase the board. I just have to illustrate this thing here so that you can understand it. Okay, let's go. Now, follow me. Now, we should also understand that sine is equal to what? A sine 2 pi x over what now? Lambda. So anywhere, so I can now come here now and do it like this. I can now say the square sine over the x square is equal to what? It's equal to minus 4 pi square over lambda square, right? Sine, because sine is equal to a sine 2 pi x over lambda. So here is a, right? Here is a, here is sine 2 pi x over lambda. So it is now left with negative 4 pi square over lambda square sine. Just take note of it. I'm trying to give you a simplest approach to this, because this is a major problem to students. How to derive the Schrödinger wave equation of time independent in atomic structure in chemistry is a very important aspect. Now we come here. Now as we move, if I'm looking for, I'll make this lambda square the subject of the formula. Later on you will see why I did that. So I'll now be having lambda square is equal to negative 4 pi square, right, sine over the square sine over the x square. Is that clear now? So I already made this one the subject of the formula, right? So we now continue. Now we should also understand that kinetic energy is equal to half mv squared, right? Follow me, which is also equal to what now? Half m square v square over what now? M, right? So that if you can take from here straight down to this one too. It is easy because m, we cancel m squared to give me what now? M. Is that clear now? So we continue. So this one should be in your heart. Now remember, from the Broglie equation, the Broglie equation, that lambda is equal to h over mv, right? Which is lambda is equal to Planck constant over mass times what now? Velocity. Remember that mass times velocity is also the same thing as saying momentum. Momentum is the product of mass multiplied by what now? Velocity. Is that okay now? Very, very simple. Do not be distracted. Now I walk you through it again. Remember, I can also induce or make an inference that pi square is equal to h square over m square v square. Is that clear? Because I'm trying to move it towards this side now. Now, m square v square is also equal to h square over lambda square. What did I just do here? I only just made m square v square the subject of the formula, so they can be imputed into this equation. So I will have to erase the board to create more room for the derivation. It's a very long process, but very, very easy at the same time. So let's continue. Now I erase the board. Okay. Okay, so let's continue. Now, I can therefore now say that kinetic energy is equal to half. So anywhere I see m square v square, I can put a square over what now? Lambda what? Lambda square. Which is I'm saying multiply by a square over lambda square, right? Multiply by 1 over what now? M. Is that clear now? Very, very what? Simple. Right? So I then come here to say, now remember, there was something I did there at first. What did I do? Remember, we used lambda square is equal to this, what now? This part here. So if I cannot recall that anytime I see this pi square here and this lambda square here, I will impute everything here. But be very careful. Remember that this one is what now? So I can simply say here is kinetic energy is equal to half times h square times 1 over lambda square times 1 over what now? M. Right? So let me erase the board further. Don't forget what we are doing here at all, because it's very easy. Now, you are having 1 over lambda square, which is the inverse of this one. If it is the inverse of this one, please take note. What you are seeing here is simply working as a single unit. Like, let's say I'm having something like this. Lambda square is equal to A over B. The inverse of this 1 over lambda square is B over what now? A. I'm walking through the gradual process here. So I can even come in to say kinetic energy is equal to 1 over 2 multiplied by h square multiplied by the inverse of this one here becomes the square sine over dx square, right, times 1 over negative 4 pi square sine multiplied by 1 over what now? M. Is that clear? 1 over what now? M. So let us continue. So that kinetic energy is equal to, remember, I'll multiply. Remember, this one is working as a single unit. So here becomes, please do not forget, there is, you remove this minus here, you simply put it here. Exactly. So here becomes negative h square over, right, 2 times 4 is 8 pi square sine, then m multiplied by the square sine over dx square. Right? Now, if I want to make this the square sine the subject of the formula, right, what will I now do? Here become the square sine over dx square is equal to, it becomes, because remember we are dividing here, so here becomes 8 pi square sine, right, sine m, right, over h square. Remember there's negative sign here. So what will I now do next? Please follow me. Here becomes what now? Kinetic what? Kinetic energy. Because I know, let me erase the board to create more space here. Please take note of this derivation. Take note of this derivation. It's actually very, very easy. You practice it, you do it, you keep practicing, you keep solving. Now please follow me, let's go. Now if you look at this stuff here, I know some of you here, your problem might be, how did this one not come up, this one came down? It's actually very simple. What I simply just did here was to multiply each side with what now? The inverse of this one, which is 8 pi squared sine m, right, over the h square, which when you do it on both sides, this is what it will now be. Is that clear now? Now let's continue. Remember that total energy, right, is equal to kinetic energy plus what now? Potential energy, which is classical in classical physics. Now, kinetic energy is equal to total energy minus what now? Potential energy. So that anytime or anywhere I see this kinetic energy, I impute this one here. So here now becomes the square sine over dx square for one dimension is equal to negative 8 pi square, right, m, right, over h square. Anywhere I see kinetic energy, I put it to now be what now? E minus potential energy, then sine, right? So if this one, like what you are having here now, is for one dimension. So for 3 dimensions now, here that become the square sine over dx square plus del square sine dy square plus del square sine dz square is equal to negative 8 pi square m over h square, then energy minus total energy minus potential energy sine, right? Which we can simply come here to say del square sine over dx square plus del square sine over dy square, okay, plus del square sine dz square. Remember, when this one comes here, it becomes plus 8 pi square m over h square. Remember, total energy minus potential energy. Then you have it what now? Sine. Very, very what? Easy. Now, there's something we call Laplacian operator. Laplacian operator. Which is simply as saying, remember, I can factorize this sign out. And now give me del square over ds square plus del square over dy square plus del square over dz square, right? Remember, here is sine, here can give me plus, right? 8 pi square m over h square. Remember, total energy minus potential energy sine. So what you are seeing here is called Laplacian operator, which is something the square, which is what you are seeing here, sine plus 8 pi square m over h square, total energy minus potential energy sine. And this marks the end of this particular video for time independent. This is what you are seeing here. Now you know what we call this sign here, a Laplacian operator. All these were all the derivations, were some of the derivations of the, remember, under Schrödinger wave equation we have for time dependent and time independent, right? There is so much that we need to know, but this is just the first part. For those of you who want a private tutoring or more explanation on this, you can do well to send me a message via this WhatsApp line and we'll go deeper and further into that. I remain my humble self, Adrenaline, the Bazooka Prophet, BSc, MSc, and PhD in chemistry. Thank you and God bless you.